You're on mute, Pradyot.
Okay. Hi everyone. We were discussing about the Dirac spinor and the different types of major and like spinors, like the major and Dirac spinors and stuff like that last week. And this week is going to be some sort of continuation from there. So the Padawan will be taking over this particular episode of Talking Physics. And yeah, so we will be going through uh, some cool stuff about spinor kinematics. So essentially, what happens is, okay, I'm sorry. Yeah. So essentially, what happens is, if you remember from the last talk, you can write down the momentum of a massless particle. Okay. Massless particle is like it's moving at the speed of light, and you have the momentum. Sorry. I mean, okay. Should I start new notes? Okay.
Yeah.
Or like, should I
Oh,
just
this is
continue?
actually good. We
I
can just parse it more slowly.
Yeah.
Yeah. Okay.
So
So cool. I
cool.
just continue over this.
Yeah.
Yeah, yeah.
Sounds good.
Okay. So yeah, so you have the massless momentum of a massless particle described by P alpha alpha dot. Please don't worry about this alpha alpha dot right now. Okay. So if you write it
So
down
actually,
in terms of the sigma the polymatrices, so you multiply the momentum with the polymatrices and then add all the individual like P naught sigma naught and then P1 sigma naught and then sum it all together and you end up with this particular matrix. So you have the zeroth component of P plus the third component of the momentum, and then yeah, so on the diagonal, and then you have the other two in the other like diagonal, right? So essentially what happens here is your this is a complex matrix, right? Don't worry about like you know these are complex momenta. If you restrict these momenta to real numbers, then you can't end up getting any of this, and it just becomes a normal whatever approach at either quantum field theory or classical mechanics. But when you allow the complex numbers to come into play, okay, you have some pretty cool interesting observation going on. So essentially what you're doing here is I'll just give you a spoiler here. So essentially what you're doing here is you're kind of isolating all the momentum to one direction only, that is the z direction. So because understand it's a massless particle that is not I mean, this is not dynamics. This is just we're dealing with kinematics for right now. So if a massless particle can move only in one particular direction, right? Any point particle can move in one direction. So you just kind of fix that direction, and then you have this interplay between the zeroth component, which is just the energy, a representation of the total energy, and then you have the some you have the
so sorry,
third,
Pradyot.
yeah.
So far, you don't need the particle to be massless at all. Like the first line, you can
Yeah.
do with any momentum. That's just an identity,
Yeah.
right? So if I
So
have
you have
P0 to PT, and then I just dot it into the sigma matrices like this, I get the following spinor object with mixed indices.
okay.
The
Yeah.
masslessness comes into play in your second line, the
Yeah.
determinant
Mhm.
0, right?
So
Because the
yeah,
determinant would be, yeah.
okay. So when you have the determinant, when you take the determinant, for a massless particle on because of the on-shell condition, that is the energy is equal to the momentum square by c. Okay, you have the determinant is zero basically,
You
and
probably want to
then
add one more point there, which is that if you compute the determinant, you'll get, p0 squared minus p1 squared minus p2 squared minus p3 squared. Basically, p mu, the.
Yeah.
So,
uh-huh.
I mean, you could just go
Right.
up, like under the determinant, you could just write that this determinant p is equivalent to p sub mu, p upper mu equals 0, like the contraction.
Yeah.
Right?
Uh-huh.
So normally that would equal m squared. That's like the mass shell condition, but when the mass is 0, this would be 0.
So it's of the form of this.
Yeah, exactly. And that
Mhm.
equals,
And then, yeah.
generically,
So,
that
and
would
then
equal m
this
squared.
will
M
reduce
squared, yeah.
to 0. Yeah.
But yeah,
So
Yeah, but now what happens is that it equals 0. And this was just like, for a recap, this was how you connect the Lorentz group or the Poincare group to SO2C,
right.
right?
Yeah.
So instead of using the metric, which is invariant under Lorentz transformations or covariant under Lorentz transformations, you use the determinant, which is covariant under SO2C transformations.
Right.
And now the line that you write down beneath the determinant, why can you do that?
So once you write down the determinant is 0, then you can actually split out
Right.
the momentum into two things, lambda and lambda bar. I mean lambda
Right.
and
And this
lambda
is a
tilde.
consequence of what?
This is because you're taking the complex space into the like allowing complex numbers to represent momentum.
No,
So-
no, it's because the determinant is 0. So the fact that you can split it means
Okay, yeah,
that
yeah,
this has a
uh-huh.
lower rank, right? So if it had full rank, you couldn't do this,
Okay.
right? So this is
Yeah.
why it's important that you have a massless particle. So in many ways, a wild spinor is a square root of a massless, like of a null momentum.
Uh-huh.
And it's only possible because the determinant of that matrix is 0. And that's telling you that there's, this is not full rank, it's degenerate.
Yeah. And then these two objects are called spinors. These are two component objects. So if you have a 4 by 4 matrix for your, you have a 4 component matrix for your momentum, it splits into two component objects, which are called spinors. And so essentially you represent the momentum in terms of spinor variables. And what are these spinor variables? Like, you'll actually see how they kind of linearize the gauge redundancies. So this basically you're kind of introducing some abstract term here to get rid of like all the complications in your Feynman diagram right in this particular step itself. Right? Am I right? Vasudev?
Well, I mean, it gets rid of some complications for some questions. I
Okay.
mean, generically, there's just going to be, whatever it's going to be.
Okay.
Yeah.
So okay. So lambda tilde is so you impose the Hermitian condition. That means lambda tilde is equal to so lambda tilde into lambda conjugate is equal to plus or minus 1. Sorry. So basically, lambda tilde alpha dot lambda inverse. Okay. Leave it. So it becomes equal to plus or minus. So you just get this particular relation after you impose the Hermitian condition, and thus you can write down the lambda the product of the spinors in terms of brackets, two kinds of brackets. These are called angle brackets and these are called square brackets. And then you just have this product, and you have this thing, the Dirac spinor here.
The epsilon symbol, the Levi-Civita symbol.
What?
The Levi-Civita symbol.
Okay. I mean.
So just to tie this back to what we were discussing before, this is basically the metric, the SO2C space, as in this is part of that metric, as in this transforms covariantly under SO2C transformations. So, yeah.
And then you have covariant. So these transfer. Yeah.
Exactly.
So these
under SO2C, these products are invariant. These angle and square products are invariant.
Yeah. So and then you have so because you see these angle and square brackets are antisymmetric in nature. So you essentially you take you change you flip the indices and then you get the negative of it, and then the angle brackets of the same index repeated twice is zero, right? The angle and square bracket, and then you have okay. So like just keep a hold. So essentially, these angle brackets are, the Mandelstam variables which correspond to the sum of the, moment of, you know, uh, uh, the various particles can be written in terms of the angle and square brackets as just a product of the angle and square bracket. So you'll see an interesting consequences of this. These happen to be zero in certain special cases. Okay, so right, so like let's just hold on this for a second. Yeah, and so apparently, like it turns out that your spinor, the lambda, can always be written as a linear combination of um, two linear index. Two linear independent spinors. So in that sense, so when you bring in this, the fact that you can have two linear independent spinors, then you have this kind of relation. This is related to the boundary operator. So in so yeah, I don't know how to exactly put this across, but essentially, so you have the various spinors. So whenever you change the sign, like whenever you write a new spinor in terms of like two existing spinor, you're always like and then you flip the indices of these two spinors. So you represent lambda j in terms of I and k, and then you flip the sign and it becomes a negative term. So in that sense, when you like kind of add them all up together, you have the relation which is called the Newton identity. So it's
Yeah.
basically
Do we
very
want to
simple.
try and derive this? It's actually a nice exercise. It really has more to do with the epsilon symbol in two dimensions. So in some sense, it's the fact that you run out of indices.
Oh,
So
okay.
epsilon ijk pk. So you take an expression like this, and then you antisymmetrize through everything. You basically find, so okay, you have to take another product because these ij brackets means that you have pi, pj, pk, right? So epsilon ij, pi, pj, and pk, right? Even though this k index is uncontracted, because of the way the epsilon symbol works, like you can take this sequence of antisymmetrizations and you get zero basically because there aren't enough indices for there to be independent quantities, right? There aren't enough indices, and the fact is that epsilon essentially has only two non-trivial components. Epsilon 1, 2 is 1, and epsilon 2, 1 is -1. You see? So you basically can only have alternating signs. You can't have anything else. So this is actually a somewhat simple identity if you wanted to prove it.
I was just going through this. Like the first thing that I saw thought of when I just saw this formula is like you have simplices and you have the boundary of a triangle, right? So your that identity, that particular identity is exact, almost the exact form here.
So
So
what's the
yeah, so I was
triangle
just
then?
thinking in terms of like boundaries, and this being the ij's being some kind of differential operators, and you have you basically fix the boundary of the 3 points ijk. So that's the kind of thing that was going on through my head. Yeah.
Yeah, I
So
can almost see
and
that. I just don't see what you're.
yeah.
I mean,
So you want
the
me to
thing is,
write it down?
yeah, I mean, I'm trying to see that, but honestly, I
Okay.
don't see why ij is going to be a differential operator.
Okay.
But
One
anyway, we
second.
don't have to dwell on that. In the end, it's not
Yeah.
that.
So this is the
It's
relation
important
I
to
was
remember that.
talking about.
I see.
Yeah. So this is the relation I was talking about. So you see the triangle here. the d0. So yeah. So you have the second derivative of 3 points, and then you have the boundary of 3 points, and then you have this particular relation. So that was the first thing that came into my mind. So when I
right, except there's three objects. I mean, here I have 0, 1, 1, 2, and 2, 0. But there I would have 1, 2, 3, 2, 3, 1, and 3, 1, 2. It's almost there, but there's you see this lambda k coming out here, but then there's a lambda k, lambda j, lambda I, which is what makes it slightly different. So yeah. Anyway, it's close. I mean, it's a good way of thinking.
Yeah.
There is something to find if you keep going down that rabbit hole. But anyway, that's for later.
Anyway, yeah. So so it turned out very interestingly that the amplitude of the scattering amplitude for n particle n gluons, okay, where there are 2 negative gluons and the rest are positive, can be written down in this formula, right? Nobody knows how this works exactly. So you just have the negative signs on the top in the angle bracket, and you have the rest of the terms here.
Right, so these are called maximally helicity violating amplitudes at tree level. So it's called an MHV.
MHV.
Yeah.
MHV, yeah. So wait, I'll just write it here.
And Park and Taylor derived this basically by resumming a very, very large number of tree level Feynman diagrams.
Yeah, so
ridiculous how many actually act as.
So you just so basically people just sat down and wrote around they computed around 30 pages of Feynman diagrams, and then they sat down cancelling everything that was redundant manually, and then they figured out that hey, this formula actually works. And they came to this. So it was normally in a QFT course. I mean, you just solve for like maximum how many orders? 2 orders of Feynman diagram, or
well, no, this is
maximum
all,
3.
So well, I mean, it depends on what you mean, but this is still tree level. It's just that what you don't do is go and look at gluon scattering beyond maybe 4 particle amplitudes. And that's because when you get to 5 particles, it's the kinematic data, so color data, in addition to the kinematic data, just leads to a lot of contractions you have to consider. Yeah, so even if you take SU2, you'd have a lot of diagrams. And then if you take SUN, then it's just it's just going to lead to 30 pages just for 5 particles. And that was where you start. This is where these people started. It turns out this is true for much more generic set of diagrams, and then there's a reason for that, which we'll discover.
Yeah, so I mean, there's so people are finding more mathematically deep reasons for this particular random occurrence. So that's where like mathematical physics is headed at right now. So where you're trying to see, you find out that a certain Feynman diagram represents just the summation of all the Feynman diagrams put together. So you just wonder why this Feynman diagram is a good representation, and then it turns out to have some deep geometric connection, and so that's where math is headed at, right?
Yeah, I mean, again, to be clear, it's not one diagram. This is like many diagrams contributing to these amplitudes.
Yeah. Mm-hmm. And then so this is So this is the next part. So then after bringing in the Lorentz group, I'm just trying, talking about the kinematics. Then you have something in the Lorentz group called as the little group, which basically leaves your momentum invariant, right? So what is Lorentz group? So you just have a set of all the rotations and the pulls, but all the kind of little operations that leave your momentum P mu matrix invariant are called the little group. So when you try to talk about, so what we'll do is we'll try to talk about the spinors in terms of little group, and we'll see how that leads us to a couple of interesting results. Okay, so yeah, so essentially, as I mentioned before, because of this, because you have a massless particle and because there are no interactions, there are no dynamics, you can fix the massless particle to be moving only at like in the z direction. So this first component represents your energy, and the fourth component, that is the third, the third spatial index, represents your momentum, right? So when you write down uh, the particular momentum
So
metric.
wait,
So
could you guess why there's an
yeah.
I there? So if I just thought about
What?
space-like or time-like particle, let's just say time-like vector, then clearly I can imagine that there's some set of rotations in space that would leave it invariant, right? So that would give me, if I take a vector in 3 dimensions, I would get SO2. Or no, I would get even, so if I took a 4 vector, then I would get SO3. And then if I took a 3 vector in 3-dimensional space, I would just get SO2. And I'm rotating, like I pictorially imagine rotating around this axis. But why is there an I here? Can you guess? Like what introduces this translation like part?
It, like invariant or something.
No.
It
So
leaves
I mean,
something
yeah,
in
sure. But where does it come from? Where could it come from?
the angular. So if you have, so it's basically the helicities and the internal symmetries of the particle, the internal dynamics of the particle, such as the gauge redundancies and all this kind of stuff.
No,
It
not quite.
to
I mean,
some.
you're right that the
Okay.
gauge redundancies relate to the translation part. And
Okay.
there's a subtle reason as to how, but really it just comes from the fact that you can do boosts in space-time. So
Okay.
you don't just have rotations. I'm just saying, imagine pictorially, I have a vector in 3D. Wow, okay, how am I going to leave this invariant? I'm just going to rotate it like this. Okay, I have a 4 vector, then maybe I can do some more rotations so that, okay, it'll give me a rotation group, but those are all compact, right? They're SO something. But when you have this I, it makes you wonder, okay, so what could I do, right? The fact is that if you have a null vector, you can do boosts that would leave it invariant. Right? It's kind of the reason why a massless particle doesn't experience any time dilation, any time at all, right? Because there's some boost that would just leave it completely invariant. And that's the I part here. So it basically comes from the boost. And together they form this kind of Euclidean group.
Yeah, just I'm adding this to my own notes.
Sure.
Okay. So, yeah. Yeah. So essentially, when you have the finite, so when you're talking about the kinematics of the particle, I mean, when you're talking about the little group, and you have finite dimensional representations of this little group. So I mean, as usual, groups are abstract. You don't know what the groups actually are, but you have some sort of representations of group, and if you can write the group representation in a finite, that is n by n matrix, then you so the little group corresponds to the eigenvectors of the rotation subgroup, like as Vasudev said, like it's the all the kind of like so the rotations that leave the net momentum invariant. So you can have so it turns out that you can write down your the spinor lambda in I mean you can change lambdas in such a way that you leave the momentum invariant. So where t is just another parameter, right? So you have this kind of
I would actually think that you have an inverse on the lambda bar transformation. Just because if it's going to leave P invariant and P is a product of lambda and lambda bar, then I would want P and T bar to cancel.
Yeah, so it has to be unitary this thing, right? So okay, so I'll just write down.
Well, yeah, that's
T bar I is equal to 1. So this is the major condition for T. This is the only condition for T. So T can be anything arbitrary, but like it has to, cancel out.
Right, T bar is essentially the inverse of T.
Yeah. Okay. Okay. So yeah.
So there's another thing we
However,
should make clear here, which is that you're not really representing the little group here. You're only representing some subgroup. This is not a faithful representation. And there's subtle reasons for that, but they connect to gauge invariance. So in some sense, you declare that the massless representations, the helicities, are just coming from the rotation subgroup of the little group. Because otherwise, you see, it'll be a bit of a mess. You have translations and rotations, they don't commute. So if you wanted to have simultaneous eigenvalues, you couldn't. So you have to choose, are you going to represent translations or rotations? And you wouldn't have just discrete labels. You'd have continuous labels once there's translations, right? So what you actually do is you say that I want to declare the action of those translations on these states to give me 0. Right? So the physical state condition is that those translations do nothing. And this is what will lead to the linearized gauge transformations. I can shift polarizations by constants times momenta, and that those will annihilate amplitudes. So
yeah, I mean, so anyways, like so for particles with so we talked about just massless particles so far, right? We didn't talk about like particles with spin. So particles with spin have an extra kind of you know, degree of freedom apart from the rotation subgroup, right? So and you can represent the it turns out that you can represent the polarization of these particles in terms of lambdas. So in as you can see here, your E plus is for the positive polarization and E negative is the negative polarization, and you can as you can see, so you can write it in terms of like some so this is this new here, I mean this, I don't know how to, I don't know what
eta
that is called, right?
whatever.
Yeah, eta. Yeah, okay. So anyway, so this eta here is the something that is like the metric. It is called uh, the declare what reference spinor. Like it's something like the metric. So where you declare all the you know, the eta alphas to be, you know, the same for all particles of that particular interaction. So you can just fix the eta alpha, and then you have only the interaction between the lambdas of various particles. So yeah, so this is just to make sure that the polarization can be represented in terms of alpha and alpha dot. So this is just because lambda is a spinor, it has only like one subcomponent. So you have yeah, so just
So
some
in
geometric
principle, you could actually take this, you know, starting from the standard picture where you have the polarization vector, and then you use the Pauli matrices again to get this object. And then you have a further condition that lets you realize that you can write this as the following product when you translate all your normal identities. So this identity you've written there with P alpha alpha dot E plus, you can write that as P mu E plus mu equals 0, and P mu E minus mu equals 0. And then you know how P splits. So you can work out how E should split, like, you know, this E alpha alpha dot should split given that. So if you know that this is going to be,
okay.
you see, you know that this is going to be annihilated, right? P mu E mu equals 0. So then you know that P is just a product of lambda and lambda bar, right? You know that plus and minus have to have one or the other helicity, right? Which means that you know that E plus should be proportional to lambda, bar, right? So that you can annihilate P alpha alpha dot. Then same thing with E minus, right? So that you get this identity that you have this square bracket.
Yeah.
Same thing with lambda minus, and then you just cook up the rest, right? You create this reference spinor, and then you normalize it, right? So you normalize it so that it has unit, the analog of unit length, but it's null, so it's kind of a weird thing to say. Anyway, the point is that this eta is doing the same thing that you normally have in the polarization vector. The polarization vector is always just coming with a redundancy that corresponds to shifting by a momentum.
Right.
But now you see you don't really have to shift by a momentum whole. You can shift by just sort of square root of it. And that
Right.
shift is basically your
Uh-huh.
spinors, your wild spinors.
Yeah.
And that's what you're coming to. Right? So
Okay.
the point is that it doesn't matter what the reference spinors are because I can keep shifting them. I can define a new one.
Uh-huh. So is it like the metric? Because like
No.
so I
So
mean
it's not like so the metric is in some sense a covariant object that transforms sort of homogenously. This thing
oh okay yeah
homogeneous. It's a shifting. So
okay yeah
yeah.
got it yeah. Alright. So anyways you can yeah so anyway so you can represent the polarizations in terms of the spinors, and then you have because the polarization is transverse to the momentum, so in the sense the electric and magnetic fields are like always transverse to the direction of the propagation of the photon. So you have p which is the momentum p times the polarization to be proportional to lambda tilde and lambda tilde, and so which is zero, right? So because uh, you have so you don't have a momentum when you talk about like uh, uh, whenever you talk about the polarization. So the polarization doesn't indicate the momentum. It's like essentially this equality sign here. So you have the same thing for the box and the square and the angle brackets. Okay. So yeah, anyway, so as I was talking before, like the eta is arbitrary and it can be decomposed into two components. So one component is dependent on the lambda, and so when you transform any, so because so how can how does eta represent the kind of redundancy that Vasudev was talking about, right? So when you transform eta into eta dash, so you can represent eta dash in terms of component of eta, that is the old thing, and then the other component which is lambda. So eta and lambda are now independent of each other, and so yeah, you consider eta and lambda to be independent of each other, and you can always kind of write this kind of transformation. I mean, you want to explain something about this, Vasudev?
Yeah, well, this is just what I was trying to say before. So normally when you have a polarization vector, you know that you can shift it by the momentum, and that should leave your amplitudes invariant. The reason for this is that it came, so you can think of it as coming from one of two things. You normally could think about it as coming from gauge invariance, the linearized representation of gauge invariance. And so this would be how you derive word identities. Or you can think of it as coming from the fact that you have these translation parts of the little group that you've declared won't affect the representation. So let me put it another way. Particle states are unitary irreducible representations of the Poincare group, right? And in particular, they're representations of the little group, right? But massless particle states, helicity states, are not faithful representations. So they're degenerate representations, which means that certain generators just annihilate them. They're not represented at all. And these generators are the ones associated to translations, right? But not literal translations. I mean, they look like that, but they really came from this boost part. Anyway, this translation part is what's giving you the shift in the polarization. It's giving you the shift in the polarization. And then what you're saying is that I can take this polarization vector, write it as a two index spinoral object, which has mixed indices, dotted and undotted. And then you can split that in terms of a reference spinor and a wild spinor associated to the momentum. Now, you do that because you want the contraction between the momentum and this to equal 0, right? And if you have this reference spinor, you're guaranteed that it'll happen because square bracket lambda lambda, square bracket lambda tilde, or angle bracket lambda lambda is 0, right? So that's why you get this structure. And then this is the denominator is just normalization. And then you can say, where does the shifting go? Well, the shifting goes to the etas. Why? Because the lambdas are representing the helicity part, right? Lambdas are transforming under what was the rotation part, like the t times lambda, t inverse times lambda twiddle, to leave p invariant, right? So you want to put the shifts into this arbitrary object, this eta, and then this is sort of equivalent. It's just a square rooted version of your old exercise in field theory with just vectorial quantities. Now it's spinors. And I think you're going to show this, but basically once you plug everything back, you can actually show that you're shifting the polarization vectors. So when you see this alpha alpha dot, you can immediately replace it with a vector index because you can use the Pauli matrix. And you see that it's actually shifting this vector by the momentum, right? Some proportionality factor that doesn't really matter. This p over a, that's just some arbitrary thing.
So you have the momentum here.
Yeah, exactly. So you see, this is exactly what you would have had in sort of the more conventional treatment, that you can shift the polarizations by something proportional to the momentum, and amplitudes would remain invariant. Yeah, and that's the manifestation of the gauge transformations. Now, it's worth pausing and thinking about how this is actually very strange. You see, in some sense, without knowing that you had a gauge theory, just knowing that you had these massless particles and that massless particles sit in a degenerate representation of the little group, you can discover gauge invariance, right? And in fact, Weinberg took this to mean something much more. He took this to mean that essentially everything you do with fields is all just spurious. Like he even thinks, all this curved spacetime stuff is just all spurious. Really, you just have coherent states of gravitons. Right? It's like the effect of all of your backgrounds are just some coherent states, and then you should be able to derive everything from the perspective of tree-level amplitudes. If you're just talking about the classical theory, you should be able to derive everything from the perspective of just these tree-level amplitudes. So he wrote this very wonderful paper. We can cover it next time, called "Low Energy Gravitons and Photons," where he proves the conservation of charge in electromagnetism and the equivalence principle in general relativity. This is super underrated, but he proves the equivalence principle.
Yeah, I think we kind of did this at the center around a couple of years back, I think.
Yeah, maybe. Yeah, I think so.
Yeah,
We had these soft theorems. Right. So the thing is that he just says, let me couple fields randomly, like I give them different coupling to gravity, right? That means that they have different coefficients in these amplitudes. But then once you plug it through this soft, you use soft factorization and you use gauge invariance, you show that all those coefficients have to be equal to each other. And from that, you can deduce that gravitational inertial mass is the same. Right. So, but his starting point was really analogous to what we just discussed, that there's some degenerate representation, there's that translation part that doesn't get represented. You see, which is very different from saying, I know that there's a field theory, I know that there's diffeomorphism invariance, and then I'm linearizing diffeomorphism invariance, and then I'm using LSZ, whatever. So that's something that, one should ponder. And it's at the heart of this entire amplitudes approach. So to these people, they don't know about, they say we forget about fields. We compute the amplitude, and then we look in some textbook and we see, oh, this was an amplitude of some such theory, right? This is a lot of what they do, right? They find, oh, this is a bi-adjoint scalar, or oh, this is a Yang-Mills amplitude, and then they find very bizarre relationships. They say, they find that somehow gravity amplitudes look like the square of Yang-Mills amplitudes, where you take away the color part. They find that Yang-Mills amplitudes look like the square of these bi-adjoint scalar amplitudes, somehow. All kinds of weird things like that. So this is what's at the heart of this field. In addition to that, they can simplify various Feynman diagram calculations, and they can do all kinds of other things. But yeah, that's what the track is here.
Right.
Yeah. So coming back, under the little group, the polarization vectors transform, as you can see, right? So you can write down the lambdas in terms of the lambdas transform according to t. I mean, this fellow. Yeah, so you can see the lambdas transforming by a factor of t, and since the polarization vectors involve two of these lambda spin-off fellows, you have basically whenever you transform the polarization vector, you transform it by a square factor of t, right? So under that, so now keep that in mind, and just do a quick jump. Okay, so your normal amplitudes of n particles, scattering amplitudes, are given by yeah. So you have the representation of the helicities on top as the indices of these integers here that represent the particles. So you can always write this amplitude in terms of the polarization vectors times the amplitude of the Feynman diagram. So this is the amplitude of the Feynman diagram. So the actual amplitude is the product of the polarization vectors times the Feynman diagram. So it turns out, so the goal of this whole bootstrap program is, to calculate, to ignore this part, forget about the Feynman diagram for now. We'll just talk about the helicities and the other, not so complicated objects. And then we'll, somehow try to find out the relation between, try to find out the actual scattering amplitude using these little easy things, right? So that is basically what Bootstrap tries to do. So that's the end goal of like all of this, like introducing.
I don't actually think that they ignore that at all. I just don't think so. They're not actually ignoring that. They're just trying to find ways to not explicitly calculate that. So they want to put implicit constraints that will determine that. I mean, if you don't do that, then there's nothing to do. Like, I mean, you just showed us how all these E's transform. You showed us what the form is. Like, there's nothing there, right? Really, what you want to say is that I don't want to actually calculate this A, mu1, mu(n). I just want to know how it transforms. I just want to know what constraints I can put on it, and then determine that in some regimes, like in some limits.
Yeah.
Generically, I don't think I would be able to do it, but at least in some regimes, I can probably figure something out. That's sort of how you would start.
Yeah. So surprisingly, if you notice the helicities as a product here, you can also see how this. So if you transform the, if you transform the polarization vectors, remember you got the t power to term here, t squared terms here. So you can see that the amplitude varies with the t factor here, right? So I mean, this is kind of weird. This is kind of bizarre for now, because like you don't know like your amplitude is not supposed to vary with the helicities. Your scattering and amplitudes is supposed to be somewhat independent of the helicities. But it turns out that these are just these can be represented as a phase space, and then most of them actually turn out to cancel each other unless you have uneven bunch of polarization vectors. For example, you have like one or two positive polarizations and rest all negative, something like that, right? When there's some kind of a imbalance, then you have this t square term. So we shouldn't really be worrying about the t square term here. Yeah, just yeah. So anyways, and then yeah. So yeah, so
I have a
these are
question.
just some
So,
of my notes.
I
Yeah.
mean, it looks like all of the a very small question. It looks like all of this is going to lead to some sort of I don't know, some sort of a bootstrapping kind of thing, right? Is it or um, like since
Yeah,
yeah,
basically.
right, okay,
So you want to be able to use symmetry arguments to fix the form
right,
of certain
right,
amplitudes.
right, okay.
All right. So okay. Yeah. So finally coming to the crux of this particular episode. So we try to calculate the amplitude for three particle scattering matrices. So we'll just take different kind of matrices, like we'll take different kind of particles, and then we'll just try to compute the scattering matrices using the angle and a square bracket. So for a three particle, remember these are massless particles, right? So so for a three particle interaction, the sum of the masses is 0. So you literally have momentum conservation between the three particles. So the sum of the three momenta is 0, and then you also have these relations, right? So they correspond to your Mandelstam variables, where this is STU. I mean, you can't really put it. Yeah. So these correspond to your Mandelstam variables, and then you have, so the P1 plus P2 the whole square is 0, and yeah. So you essentially have a system. So this looks kind of bizarre, right? You say that the momenta is 0, and then like what are we exactly talking about, right? So you also, but you also need to understand somehow that there is this kind of redundancy, that you're fixing a particular. I mean, you can't have some kind of spontaneous. Vasudev, you want to actually explain this little part out here?
You mean that you
Why
can't?
is this the Mandelstam variable?
Well, I mean, you showed us why. So it's just a consequence of the fact that if you have real momenta, you can't actually have, like, these processes are essentially such that they're kind of trivial. You don't really have anything happening. Like, you really have massless particles, and then you have momentum conservation. You can't really get them to lead to particle creation or anything like that.
Actually, in the regular KFTs, you have the the scattering amplitude of three particle is 0, right? So the expectation value of like the three particle interactions is 0. So yeah, so the same thing occurs here. So in a very physical sense, it just means that you can't have. So what is three? How can three particles interact, right? You have one particle splitting into two particles. But that can't really, you can't have a massless particle split into two massless particles. And at the same time, you can't have two massless particles coming together, colliding to produce a new massless particle which has some momentum, right? So because of this kind of constraints, right? You just
essentially
whole thing 0, right? Okay. So yeah. So yeah, I mean.
Sorry guys, this is a jumping off point for me. I unfortunately have to, but yeah, I look forward to seeing where this goes.
Yeah.
Have fun. See you later.
Yeah. So anyway, so if you just try to compute the angle, and so suppose if you set the angle brackets of 1 to the angle brackets are 0. I mean, so angle brackets are not 0, then your square brackets have to be 0 for all combination, right? So if you look at it here, so you say 1, 2 is not 0, then all the square brackets here have to be 0. So you can just do basic distributivity you can use the distributive property to show that everything is actually 0. Like either all the square brackets or all the angle brackets are 0. So you just write down this term. So this term is 0, right? This represents P1 square. Okay. So this term is 0. So anyway, so you use the brackets here, and then you write down so you just distribute. Remember, it's like this distributivity is not like just regular distributivity. You have some kind of Leibniz rule acting here, right? As you can see here. So all these turn out to be 0. So you can show that actually because we define 1, 1 to be 0, right? In the very beginning, when we define angle brackets itself, we define 1, 1 to be 0. So thus you can represent everything as a product of like two same indices, and then you have a box, right? And then
Yeah.
So everything is basically zero. So if you have so essentially thus if 1 2 is not zero, then angle like the box is not zero, then the angles are zero. Yeah. So to give now so essentially this corresponds to an interesting mathematical fact. So if you have angle fact the square brackets equaling zero, then your lambda 1 is proportional to lambda 2 is proportional to lambda 3. So this means that these kinematics are this kinematic configuration is holomorphic, and then if the angle brackets are zero, then these are anti-holomorphic. So where lambdas are like just proportional to each. Yeah. So anyways, so this just implies the whole thing that we talked about. So in P1 square is 0, P2 square is 0, P3 square is 0. You have these products also, the inner products also to be 0. So yeah, so this is one thing, right? So when you represent the remember we talked about representing the whole amplitude in terms of products of felicities. Yeah. So you can write down this in terms of the number of like in terms of like powers, right? So you can write down 1 2 in power into the power to the power of some number. So this is so wherever is like whichever number is missing here, just write down the number there as the power. So you can write down these as some powers, and then it turns out that when you solve for all these powers, because these powers actually correspond to the helicities. So if you see here, so this is the helicity of the third index 3, the third particle. So this 1 2 term here corresponds to the helicity of the third particle and stuff like that. So you have this whole you have this minus 2's product coming here, right? I mean the minus 2 come here. So okay, so like you can solve, basically you can solve for the you can represent the helicities in terms of n, where n1 is just the helicity of 1 minus helicity of 2 and 3 and so on, right? So okay, so now okay, so it turns out that n are always integers, right? Because see, if you have boson, so there are two kinds of fundamental particles in nature. One is boson, and that is fermion. So if you have boson can always occur in single numbers. But if you talk about fermions are always coupled or paired with each other. So if you have so if you have a electron, you have like the other the positron compensating. So these electron positron couplings are always happening. So because of this, so you talk about 2, right? So if you have spin half particles, so you have 2 spin half particles, and then the net polarization is always 1 in some way, right? So yeah, so basically that's the whole thing about the n. So you have already added a huge constraint to your limits to the kind of helicities that you can take, because you're restricting n to just integers using a physical fact, right? So now okay, so okay, so it turns out that this particular constraint is imposes like another constraint on the kinematics of a particle. So there are basically the mass. Okay, so this just skip all this part. Like this is a little yeah. So this this essentially means that you have some kind of redundancy. You have some kind of gauge redundancy in massless particle, which are scalar. Oh yeah. So this is the important thing. These are all like scalars, right? So when you're talking about the so far we were talking about scalar. So when you have the massless scalars, because you have some kind of a like a redundancy, right? So you have some kind of fixing, right? You have some kind of fixing that is happening because of the like using the conservation of momentum, and then you have this n is belong to integers term, and using all these fixings, you still find out in scalars, right? They have some kind of redundancy happening, right? And also this, what does this mean in terms of okay. So you can always write down the Lagrangian in terms of like something very simple, the action or the Lagrangian in terms of something very simple. You don't have such complicated. So you don't have things like so where phi is the field, right? So you don't have terms like with the differential operator. So derivatively coupled. You don't have derivatively coupled term, and even if you do, right, they all like you can always cancel them out in some way. It's just, if you come across these terms, that means you're simply writing the Lagrangian wrong,
Right.
so you can always kind of, so this so for like, for example, like gluons and stuff like that, if you look at the kind of interactions that are happening, most often than not, because you're trying to deduce the field from the data that you have. Okay, you invent all these like terms to just fit in your Lagrangian, right? You don't really have some kind of you you it basically you end up with a very complicated Lagrangian. Whereas when you use the angle and square brackets, you know that you cannot have this kind of term, because they represent they are not scalar. You find out that they are not scalar, and then therefore you're just writing down this Lagrangian wrong, and therefore so you can always reorder it. Essentially, that's like that's the major use of you know writing down in terms of spinors. So you just don't have to write down the Lagrangian anymore. You just write down everything in terms of the spinors and the other parameters that represent the particle, and then you expect, you just get some sort of scattering amplitude by here, right? For scalars, I mean for vectors, okay, it turns out that these are fixed, right? So these so because okay, so basically you don't have so essentially you don't have cubic interaction here, right? So for scalars you had like zero interaction, and then for vectors you have square interaction. So you have interactions of the form phi square and stuff like that, which is basically what your Maxwell equation, like Maxwell Lagrangian looks like. But then for tensors, it turns out that you cannot you just have quadratic this thing. So you have, I mean, you skip the cubic sorry so you skip the cubic and you just go on to the biquadratic exponential. So one second, just yeah. So you just have a 6 derivative cubic interaction. You don't have a 4 derivative like quadratic interaction anymore. You just have a 6 derivative interaction. So like you have a 2 derivative interaction here in terms of your like vectors, but then you have a jump to a 6 derivative. So you don't have the 4 derivative, even if you're saying there is some sort of even coupling that is happening. So you can only have like even number of derivatives of interaction. Okay, you have like this is a very curious fact, right? This is the most interesting fact that comes about here. So maybe in the next episode we'll like talk more detail about this. So you just jump on to the 6 derivative interaction, and then what does this mean? This, if you look at this, so if you talk about tensors and if you talk about helicities in terms of tensors, you actually end up talking about gravity. Okay, so you have the expressions that you write down exactly correspond to your Riemann, the Riemann curvature tensors.
Right.
So you have, so you can also imagine it as some kind of a geometry, right? That is the reason why I referred to the the triangle thing before. So because when you talk about the boundaries, so when you talk about geometries, so you always have so if okay, so the boundary of a triangle is 0, and then the next dimension you jump to the next dimension, or you jump to the the next polygon. Like I don't know how it works out, right? But it's basically very visual in terms of like the geometry. So you can have like six. So after 3 comes, after 0 comes 2, then you have 6. So that is some kind of a direct visual representation happening here. So maybe next time we should talk about how exactly these angle and box brackets correspond to the Riemann curvature tensors and the Christoffel symbols, and then stuff like that.
Right.
So yeah. I mean, I skipped more. Okay, so in case you're wondering, yes, I did skip most of the math after like so after just talking about the scalars, because like so you can basically write down everything in terms of just know that you can basically write down everything in terms of square and angle bracket. So all amplitude can be written down in terms of square and angle brackets, and then they just somehow happen to cancel each other out, right? So yeah, that's all needed for now. And yeah, Rahul, do you want to conclude?
Yeah, I guess so. Yeah, I'm pretty curious as to how so the part where you said you talked about the 6 derivatives of the cubic thing, right? Part is still a bit unclear. So probably when we see how it connects to the Riemann tensor and we dig more deeper into that, I'll get some more clarity on that. But overall, yeah, this is pretty interesting.
Yeah.
Yeah, need to ponder over it a bit more. Yeah. Okay, so I'll stop the recording here.
Yeah.